Welcome Bella Tobin from Oklahoma State University to our number theory seminar. She will give us a talk on reduction properties of post-critically finite polynomials.
Thank you so much for the introduction and for inviting me to speak. So my research lies in arithmetic dynamics, and in arithmetic dynamics, we're interested in number theoretic properties of algebraic points under iteration of a rational map. So let's let K be a number field, and we're going to consider a rational map F over K. We define F to the n to be the nth iterate of F, so F just composed together n times. And for any point alpha, we define the orbit of alpha as just the image under all the forward iterates of F. So it's just F to the n of alpha for any value of n. And then we want to classify these points based on their behavior under this iteration. So we say that a point is periodic of period m if after m iterates, we get back to alpha. We say it's of exact period m if this is the least number, right? So maybe if something is period 2, it could also be of period 4 or period 8, but we want to consider the smallest such m. Similarly, we say that a point is pre-periodic if eventually it loops back onto the same orbit. So maybe if f to the k of alpha is equal to the f to the m plus k of alpha, and then we say it's pre-periodic of period km. And if we say a point is pre-periodic, we can allow that to also be periodic by just having k be equal to 0. And then finally, we say that alpha is a wandering point if the orbit is not finite. So often we want to describe maybe a map that has the same dynamics as a different map. And sometimes when that happens, we say that those two maps are conjugate. So if we have a polynomial or any rational map in K, we say it's conjugate to a map G if G is equal to f to the phi for some phi in PGL2. And here we define f to the phi as just phi of f of phi inverse. This is essentially just a change in coordinates. So this conjugation works really well with the iteration of these points. So if we have a point that is pre-periodic of a given period for a map F, then its image under this map in PGL2 is also pre-periodic of the same period for any of the conjugate maps. So if we want to maybe describe the dynamics of a certain map, we might want to do so up to conjugation. And so we're just going to consider these conjugacy classes of these rational maps. So in arithmetic dynamics, the orbits of the critical points play an important role because the orbits of the critical points largely determine the dynamics of the entire map. So we're going to consider the critical set of a rational map F. We say that a map is post-critically finite if every element of the critical set has a finite forward orbit. So that means that every critical point is either fixed or pre-periodic or periodic, but the critical points can't be wandering. So an example is this cubic polynomial 2z cubed minus 3z squared plus 1/2. This polynomial has critical points 0 and 1. The orbit of 0 is just 0 and 1/2, and that's actually a 2 cycle. So 0 will map to 1/2, which maps back to 0. And the orbit of 1 is just 1 maps to 1/2, and 1/2 is a fixed point. So we see here that this is a post-critically finite map. And in general, we're really interested in post-critically finite maps in arithmetic dynamics. So we want to be discussing these reduction properties of post-critically finite maps or of any maps. And so we need to introduce some notation so that we can talk about reduction. So for the remainder of the talk, we're going to let K be a non-Archimedean field complete with respect to some absolute value V. We're going to let OK just be the ring of integers as standard. P will be the maximal ideal. K the residue field, and we're going to let tilde f be the polynomial in K obtained by reducing the coefficients modulo P. So how can we reduce rational maps? Well, suppose we have a rational map of degree D. We can always write this map in a normalized form, so we can write it as a ratio of these two polynomials that have integer coefficients, no common factors, and at least one coefficient has absolute value 1. And once it's written in this normalized form, we can we can define the reduction just by reducing each of those polynomials. So let's look at a few examples. We're going to consider the polynomial 4z cubed minus 6z squared plus 1, and we're going to consider this both in the 3-adics and 2-adics. So when we reduce it in the 3-adics, we get z cubed plus 1 over 2. And when we reduce this exact same polynomial in the 2-adics, we just get 1 over 0. So we can see that that was sort of a bad situation that happened there, because when we reduced it, it greatly changed the polynomial, and it will have greatly changed the dynamics then. Now let's consider the rational map z cubed plus 3z over z to the 4th plus 1 in the 5-adics. So here, when we reduce modulo P, we see that the denominator factors into z squared plus 2 times z squared plus 3. And so this is actually just z over z squared plus 2. So since these reduced polynomials shared a common factor, then when we reduced it, the map did change greatly. Okay. So we're interested in seeing how these rational functions reduce, and if they reduce nicely, then some of these properties, the dynamic properties, are maintained in this reduction, and if it doesn't reduce nicely, then we can we kind of say that this map has like bad behavior at that prime. So we say a map has good reduction if the degree stays the same under the reduction. If it doesn't, then we just say it has bad reduction. So we see that in these examples. This first example in the 3-adics has good reduction because we had a degree 3 polynomial. After reducing, we still had degree 3. However, when we reduced it in the 2-adics, we had a degree 0 rational map. So that was clearly bad reduction. And we also see in this rational map here that we have bad reduction because we decreased in the degree. And so we'll be a little bit loose with language sometimes, and so we might say that if we are just considering this as a polynomial in Q, we'll say it has good reduction at 3 and bad reduction at 2. So if a map has good reduction, it tends to behave well under dynamics. So if it has good reduction, then we can get the reduction of the nth iterate by just taking the nth iterate of the reduction. And this also works when we're looking at maybe the image of a point under the nth iterate. So this leads us to believe that if we have maybe a preperiodic point and we have a map of good reduction, then that point will still be preperiodic after reduced. And in particular, say we have maybe a periodic point of exact period n, then after we reduce, then the reduced point will have period m where m divides n. So it doesn't need to have the exact same period, but it has a period that at least divides the initial period that we had. So we also know that a map has good reduction if and only if its iterates have good reduction. So if we find an iterate that has good reduction, we know the original map did as well, and vice versa. And furthermore, we know that maps that have good reduction have this nice local behavior, and that just means that the Julia set is empty. So if a map has good reduction, then its Julia set is empty. So this is really saying that these maps are locally well behaved. So we know that iteration behaves well under this when we have good reduction, but what about conjugation? So suppose we have some normalized rational function, and maybe it has bad reduction, but one of its conjugates has good reduction. Okay? That could happen, and in that case, we say it has potential good reduction. So if there is a way to conjugate a map so that its conjugate has good reduction, then we say it has potential good reduction. And if there's no way to do this, then we say it has persistent bad reduction. So if we're trying to determine if a map has potential good reduction, and we're just looking at maybe like, one element of the conjugacy class, it's not exactly clear just by looking at that one element. And so we might want to find, well, some conjugate that has like the best case possible, right? So, what conjugate should we be looking at that will give us, tell us exactly where we have good reduction and exactly where we have bad reduction. So if we specifically have a polynomial, we can always conjugate it, or find a conjugate that is monic and fixes 0. And if that conjugate has explicit good reduction, then we know all of its conjugates have potential good reduction. So conjugating to make something monic and fix 0 kind of gets us the best conjugate possible, right? So this is the best case scenario where we know like all of the primes of good reduction and all the primes of persistent bad reduction. So why do we care about this? Okay. So in addition to the reduction telling us a lot about the dynamics of the maps, we have this connection between post-critically finite maps and CM Abelian varieties. So post-critically finite maps are these dynamical analogs of CM Abelian varieties, and when we have nice properties of CM Abelian varieties, we want to see if they hold for post-critically finite maps and vice versa. So we know that a CM Abelian variety is defined over a number field, and we know furthermore that it has everywhere good reduction in some extension of its base field. So for post-critically finite maps, we know that they are algebraic outside of, well, a single well-understood family, which is called lattice maps, which we're not going to discuss today. But outside of that family, we know that all the post-critically finite rational maps are algebraic, so we might want to ask about their reduction properties. Do they have good reduction? Or, when do they have good reduction? When do they have persistent bad reduction? So you might be thinking about your favorite post-critically finite maps. Maybe you know a unicritical map that's post-critically finite, like z squared minus 1. A lot of unicritical families of z to the d plus c. We like to look at those for post-critically finite examples. And those unicritical post-critically finite maps all have good reduction. But that example, when I was introducing post-critically finite maps, I gave this example of a polynomial that in fact has persistent bad reduction at 2. So we know that not all post-critically finite maps have good reduction, and we also know that they don't all have bad reduction. So now the question kind of becomes, well, when do they have good reduction, and what conditions can we impose to maybe figure out when they have good reduction and when they have bad reduction? So if we're going to be talking about post-critically finite maps, then we might want to talk about Belly maps. So if we're talking about post-critically finite maps, we don't know all of the post-critically finite maps. So we might want to look at maybe a well-understood family of post-critically finite maps and see the reduction properties of that family. And we can build a family of post-critically finite maps using Belly maps. So a Belly map is just a finite cover going from a smooth projective curve to a Riemann sphere that's branched exactly at 3 points. And we want these points to be 0, 1, and infinity usually. Now, since we work with dynamics and we want to be able to iterate this map, then we want to make sure that we're actually already working on the Riemann sphere, and we furthermore want to make sure that the image of the branch points is contained in the branch points. Okay, that way, whenever every iterate is also a Belly map. Okay, so imposing these conditions means that every time we iterate, we also get a Belly map. And we're going to impose more conditions, and we're going to specifically look at single cycle normalized dynamical Belly maps. And this is a specific set of Belly maps that has ramification points 0, 1, and infinity, and each of those are fixed. Okay. So a single cycle, every family of single cycle Belly maps has a conjugate that is normalized. Okay, so we may as well just look at the family of single cycle normalized dynamical Belly maps. And then we have a nice formula for each of these maps. So for any integers d and k, where d is greater than or equal to 3 and k is between 1 and d minus 2, we can define a dynamical Belly polynomial as b d to the k, b of dk z as this formula here. Okay. And these dynamical Belly maps also exist, like there is a rational family as well, but we're only going to think about the polynomials today. So these fix 0, 1, and infinity. And so we know that, so the critical points are 0 and 1, and we know that those are fixed. So we know this is post-critically finite. And these also have some other nice properties. They lie over Z, and they have content 1, and they aren't monic. So since it fixes its critical points, we know it's post-critically finite. And we can actually use these to find another family of post-critically finite polynomials. So if we have any bicritical polynomial, so that's just a polynomial with 2 finite critical points. And if we have k rational critical points, then we can always conjugate it to the form a times a Belly polynomial plus c, and will remain in that base field. So this means any bicritical polynomial of even degree, or if it has odd degree and the critical points have distinct ramification indices, then we can always conjugate it to this form and remain in that base field. So this gives us a nice search space to try to find post-critically finite polynomials. So let's think about this cubic case. If we're just looking at degree 3, and it has rational critical points, we're looking just over Q and we're looking at cubic bicriticals with rational critical points, then they will all be conjugate to a polynomial of this form here. And furthermore, we know that the parameters a and c will be one of these pairs. So this gives us a nice list of cubic bicritical PCF polynomials, but this is only covering the rational critical point case. It is possible that we could have a cubic PCF polynomial with irrational critical points. And we can find those as well. So this is all of the cubic PCF polynomials defined over Q. Okay. Now when we're looking at this nice like family of cubics, we notice a few things. So polynomials 1 and 2 are unicritical. They only have one critical point. So these were previously known and these are well understood, and they also have good reduction everywhere. When we look at most of the other polynomials here, we see that most of them have persistent bad reduction at 2, except for number 11. Number 11 has potential good reduction at 2. We can conjugate it to z cubed minus 3z, and we'll get we get good reduction when we conjugate it to that form. So now we know we have a cubic PCF polynomial that has good reduction at 2, but we also know we have this, many more that have persistent bad reduction at 2. So now the question kind of becomes, well, when does this happen? Why is this happening? And can we find maybe a similar polynomial of any degree d that has potential good reduction everywhere? So we're going to go and think about these Belly maps again, because all those polynomials, all these cubic polynomials here, or at least many of them, were built off of these Belly polynomials. So if we can understand the reduction properties of Belly polynomials, it might tell us a little bit about the reduction of post-critically finite polynomials. So if we let P be a prime and we write D as P to the n times L, where L is greater than P does not divide L, then we can find some value of K such that the Belly map BDK has persistent bad reduction at P. So as long as this is satisfied, as long as for this given degree in prime P, we can write D in this way, then we know we have a PCF polynomial of degree D that has persistent bad reduction at P. And this isn't saying that, there doesn't exist a degree D polynomial that has potential good reduction there. This is just giving us this nice example that we know there's persistent bad reduction for this belly map. And as it turns out, if we cannot write D in that way for this given prime, then there does not exist a PCF polynomial with persistent bad reduction at P. That means that if D is equal to P to the n times L, where L is less than P instead of greater than P, then that means that every degree D PCF polynomial has potential good reduction at P. Okay, so this theorem is telling us kind of when persistent bad reduction exists, but it isn't giving us a condition necessarily for when potential good reduction exists. So we're going to sketch a proof of this theorem, and then we're going to look at an example of this theorem for a specific degree. So in the proposition, we see that, if we can write D in this way, so if we can write D as equal to P to the n times L, L greater than P, and P does not divide L, then we know that there exists a PCF polynomial with persistent bad reduction at P. It's namely that belly map that we were looking at. So now we're going to consider the case where D is equal to P to the n times L, where L is less than P. So let's let F be a PCF polynomial of degree D, and we are going to make it be monic and fix 0 because we know at least one conjugate does that, so we may as well assume we have that conjugate. So we're going to let the v-adic absolute value just be the extension of the p-adic absolute value normalized in the standard way. So the associated valuation is just the valuation of alpha is negative log p of alpha. And we're going to let ai be the ith coefficient of the polynomial f. Since it's monic, we know that ad is equal to 1. So we are going to assume or suppose that f has persistent bad reduction, and then we're going to obtain a contradiction, which is going to say that, well, if these conditions aren't satisfied, so that L is less than P, then we must have potential good reduction. So if f has persistent bad reduction, then one of the coefficients has v-adic absolute value greater than 1. So we're going to let alpha I be the d fixed points of f, and we're going to let gamma I be the critical points. And we're going to use Newton polygons to give us some conditions and some information about these fixed points and critical points, knowing that one of these coefficients has v-adic absolute value greater than 1. So let's first look at the Newton polygon of f of z minus z. So this is going to tell us information about the fixed points. This Newton polygon we know has at least one segment of positive slope. So that means there is at least one fixed point, which we're going to call alpha 1, that has v-adic absolute value greater than 1. So now, suppose the rightmost line segment is connecting these 2 points here. Then it's going to have slope r. So and since this segment is of length d minus I, then this tells us it has d minus I fixed points with absolute value p to the r. That means that there are exactly I fixed points that have absolute value smaller than p to the r. So now let's look at the Newton polygon of the derivative. The slope of the rightmost segment will be at least given by this ratio here, the valuation of d minus the valuation of this coefficient, the derivative, over d minus I. And we know that that's at least r. That rightmost segment is going through the points d minus 1 and I minus 1 in the valuation of this coefficient of the derivative. But we can show that using just non-Archimedean absolute value properties, that if one of the critical points has v-adic absolute value greater than p to the r, then that critical point would have to escape, right? Its orbit could not be finite because its orbit wouldn't even be bounded. Okay. So, and that's just shown just by, playing with the absolute value. And so if we know that that's true, and then we must have equality here, because this is saying that no critical point can have absolute value greater than p to the r. So that means that the rightmost segment must have slope exactly r, which tells us the valuation of I is the same as the valuation of d, so I is a multiple of p to the n. So this means we have d minus I critical points of absolute value p to the r, and all the others must have absolute value strictly less than p to the r, since this was the rightmost segment. Okay, so to reiterate here, we have d minus I fixed points and at least d minus I critical points of absolute value p to the r. And then we have I fixed points and at most I minus 1 critical points of absolute value less than p to the r. So now we're going to look at these disks centered at the fixed points of radius p to the r. Since f is post-critically bounded, we know that each of these critical points must lie in these disks. And then we're going to use kind of like a pigeonhole type argument to show that we cannot have these conditions on these fixed points and critical points. So in the disk centered at 0, because we know 0 is a fixed point, then there are most I minus 1 critical points, because there's at most I minus 1 critical points of absolute value less than p to the r. We also know that there's exactly I fixed points. So there's some other disk centered at some other critical point that contains at least as many critical points as fixed points. Okay. Now, if we conjugate and we try to move the fixed point aj to 0, then this newly conjugated map should have these same properties, but it will have fewer critical points of absolute value p to the r than fixed point, and we've shown that that can't happen, right? We know that there has to be at least as many critical points of absolute value p to the r than there are fixed points. So since that can't happen, it must have been that the only condition that we started with, that one of the coefficients has v-adic absolute value greater than 1, can't happen. So therefore, we know that all the coefficients have v-adic absolute value less than or equal to 1, and so this polynomial has persistent good reduction. So let's just look at this theorem and kind of understand what this is saying. So this is not giving us a condition for when there is a PCF polynomial with potential good reduction. We in fact know that for every degree d, there's a PCF polynomial with potential good reduction everywhere. This is only giving us a condition for when there's persistent bad reduction. And in the case where the prime is larger than the degree, or maybe the degree is a prime power, this recovers previously known results that every PCF polynomial has good reduction at primes larger than the degree, and every PCF polynomial of a degree that's a prime power has potential good reduction at that prime. Let's look at the example where degree is equal to 18. So here we're using the notation from the proposition. So P is our prime, N is the prime power, so we're writing D as equal to P to the N times L. And we'll notice that in the case where P is equal to 3, L is less than P. And so all degree 18 PCF polynomials have potential good reduction at 3. Right? There's no degree 18 PCF polynomial with persistent bad reduction at 3. They all have potential good reduction. But for all other primes, there are PCF polynomials of degree 18 that have like persistent bad reduction at these primes. And we may notice that the examples that are given here are all these Belly polynomials, and these Belly polynomials have bad reduction at more than just one prime. So even though maybe say that this one is given in the p is equal to 2 column, we know it has persistent bad reduction at 2, but it also has persistent bad reduction at other primes as well. So this is answering the question of when is there persistent bad reduction, but this isn't telling us too much about when is there like potential good reduction. So let's say that we're given a degree D and a prime P. We can build a post-critically finite polynomial of degree D that has good reduction at P. So this is saying that for any degree D in prime P, we can always find a PCF map that has good reduction at that prime. And we can prove this using that example of that cubic polynomial that had good reduction everywhere. We know that that was built from a Belly polynomial, and so we can just extend that Belly polynomial to degree D. And so what's in these parentheses here, this negative d minus 1 z to the d plus d times z to the d minus 1, that's just a Belly polynomial. It's specifically BD1. And so we can build this bicritical PCF polynomial that's very similar to that cubic example, except we're trying to extend it to degree D, and we're building it so that it has good reduction specifically at some prime. So we know that the image of 0 is a fixed point, and we want to make this PCF, so we're going to say, okay, well, we want the image of 1, which is the other critical point, to also be a fixed point. So that means that we need to find the parameter A that makes the image of 1 a fixed point and also has good reduction at P. So that means that A needs to be a root of this polynomial here. If P doesn't divide D minus 1, then all these roots are p-adic units, so we can choose any of those roots to build a PCF polynomial with potential good reduction at P. But if P does divide D minus 1, so let's just say the valuation of P of D minus 1 at P is M, then we can construct the Newton polygon, kind of a similar argument, and we'll see that there is a root out that has valuation D minus 2 times M, and if we choose that particular root, then we're going to have a PCF polynomial with potential good reduction at P. Okay. So this is specifically building a PCF polynomial that has good reduction at a given prime. Okay. So we have a condition for primes and degrees for when there are PCF polynomials of degree D with persistent bad reduction. And we know when this condition is not met, every degree D polynomial has good reduction at P. And that was sort of this main theorem that we looked at this example with for degree 18. We also know that for any prime P and degree D, we can build a PCF polynomial of degree D that has potential good reduction at P. But we haven't quite answered like the million-dollar question here, which is, can we find a degree D PCF polynomial with good reduction everywhere that's not trivial? Okay. So when we say not trivial, we mean non-unicritical and non-Chebyshev. Unicritical polynomials, we know they have good reduction everywhere, and Chebyshev polynomials have good reduction everywhere. And so we want to find these non-trivial examples in any degree that has good reduction everywhere. And actually, as it turns out, that cubic example that we started with is conjugate to a Chebyshev polynomial. So even the first example we started with that had good reduction everywhere was not really an example for this. We still do not have a degree 3 polynomial that's non-unicritical and non-Chebyshev that has good reduction everywhere. Are there any questions?
Well, are there anybody here? Any questions for our speaker?
I have a question, Bella.
Yeah.
Probably this is very naive. So these polynomials you're looking at, I mean, can you think about an elliptic curve, like the equation of elliptic curve, and like all these reduction types are you talking about? Are they like corresponds to the reduction type of the elliptic curve?
I believe so, yeah.
Okay. So like if you specifically the results you know for elliptic curve for this kind of question of like if you can fix a potentially good reduction or this kind of thing. What I was thinking is my thinking was that probably for elliptic curve, some of these questions you are asking may be known. I'm not.
Okay, so in that aspect, they're not necessarily, so while some of the things translate over from like the elliptic curves to these polynomials, they don't all. And so this is one of those things that we still aren't exactly sure if the same properties hold.
I see.
Yeah, so we know that they are like very similar, but we don't know like if all of the properties translate between like this arithmetic dynamics question and like the elliptic curve question.
But since you mentioned that these polynomials you're looking at, they correspond to CM algebraic variety. So do they correspond to CM elliptic curve if you try to like?
So
Not sure.
they're described as these dynamical analogs, but that doesn't necessarily mean they have all the same properties.
So this CM is not, is the CM same as like the CM for elliptic curve or for any other variety? Like
yeah, yes. And so they're described as these analogs. And so kind of like one of the questions is kind of saying like, well, how far does that connection go? Right? Because there are some cases where we can maybe prove something about post-critically finite maps and then recover the result for abelian varieties, or vice versa, but that's not always true. And so like in this case where we know this thing about these like CM abelian varieties, but this isn't true for post-critically finite maps.
I see.
Right, so there is this connection here, but it's kind of like digging deeper and understanding like why some of these properties hold for like on one side of the fence and why they don't hold on the other side of the fence. And maybe, the analog is not necessarily as strong as we think it is, or maybe the analog's a little bit different than how we're thinking of it.
I see. Yeah. Okay. But you kind of go in both direction. Like if you know something about abelian varieties, you try to translate that in your sense. And also like if you get to know something about, discover something new, then you translate in the other sense.
Yes. Yeah, exactly.
Okay. That's great. Thank you.
Is there another question? Well, I just want to comment on one thing to answer Manami Roy's question. There's a theorem that any abelian variety over a number field has potential good reduction everywhere. See, that's a theorem. You can find that in the paper of Sayre and Tate, for example, although I'm not sure it's originally due to them. For elliptic curves, it was certainly earlier. People like Doyring and others knew this.
Yeah.
So one property of CM abelian varieties is that they have potential good reduction at every place. So after base extending, okay, but maybe you also know the theorem of Fang-Ting that there's no abelian variety over there's no abelian variety over the integers, which means that if you take an abelian variety over Q, it must have some place of bad reduction. So that's true. That's a theorem of Fang-Ting. So every abelian variety over the rational field must have a place of bad reduction. But if it has type CM, you can base extend it so that it has good reduction. Okay?
Mm-hmm.
Yeah, I mean, you know that theorem, Bella? Yeah. Fontaine's theorem?
Yes. I don't know if I knew who it was due to, but yes.
Yeah, it's due to Jean-Marc Fontaine, the late, great Jean-Marc Fontaine. So I have just one question. I was trying to think about your F's. Let's just say it's a polynomial. And let's just say it's an integer polynomial, right? For example. So I can think of it as defining a covering from P1 of Z to P1 of Z, right?
Mm-hmm.
And question is this, if I have a prime, I can reduce that morphism. And are you saying that bad reduction in this sense means that that map is no longer flat as a morphism? See, I mean, this condition that the degree drops, that's going to screw up the flatness of that map in general. So I'm trying to translate this into a more algebro-geometric statement. So, because I'm an algebraic geometer. But I'm not sure if it's equivalent. You see, if you just think of the simple case of a polynomial map, it maps P1 of Z, the scheme P1 over Z to P1 over Z. And now you could pick your favorite prime and look at the induced morphism. And if that degree drops, that morphism will probably not be flat anymore. In other words, the overall map F will have a locus of non-flatness. So this is my question. Is that equivalent or related or something?
I'm not entirely sure.
Okay.
But that is a good question. I will look into it.
See, the other question I have is, how does this connect to Galois theory? You know, this was you mentioned Bellier. I always think about Grothendieck. And you know how Grothendieck got so enthusiastic about Bellier's theorem because he was trying to study the Galois coverings of the projective, well, for example, just the Galois theory of the projective line over a number field, for example. Mm-hmm. And so these Fs define, well, they won't be Galois, but they're gonna, I don't know. I mean, I guess my question is, another point of view is to think of these coverings from the point of view of Galois theory, right? You have I mean, it's not exactly a Galois. I mean, this extension is not Galois, but it will have a Galois closure. And when you talk about ramification, you see, that's something you always do in Galois theory. So it's a different point of view.
Yeah, that's interesting.
So I don't know what you people do in that field. So, you know, I don't know what the point of view is. You know, you think of this as dynamics. Well, that's interesting, but I'm just trying to connect it to things that are more familiar to me.
So, yeah, so I know that there are like a lot of connections like to like algebraic geometry. I'm obviously less familiar with the algebraic geometry side than the arithmetic dynamic side. And I also, I mean, I don't know in this case what you could say about the like the Galois groups or anything. Yeah, I'm not sure.
I doubt these are Galois extensions in general. I mean, you know, they'll have a Galois closure, but I don't know if that it tells you anything interesting about your F, you know, from your point of view.
Yeah, I'm not. I don't think it does necessarily, but I'm not entirely sure.
Okay. Does anybody else have any other questions for our speaker? Well, if not, let's thank her.
Thank you.
Thank you very much.